Hey guys, welcome back to our study of dynamics. Here we're talking about an inclined plane, so this will be the first of two little sections on how we deal with inclines. So we have to remember all of our dynamics and moving in one dimension and net force and all that. So here we have a ball sitting on a level surface, and it will not roll because the forces on it are balanced. Here we have the two forces, the normal force pointing up and perpendicular, and the weight of the object, or the force of gravity. So we know that these two things are equal. We won't spend a lot of time doing that, but we know that it will not roll because the forces on it are balanced. However, when we set it on an inclined plane, it actually begins to roll down, right? The motion is pointing down the ramp. And we still have to realize that the weight of the object is still pointing down, and the normal force is still perpendicular to the object. So there's some kind of net force that is pointing down the ramp that we have to account for. So when we start analyzing this at all, the force of gravity is always pulls straight down. So we have to make sure we always draw this pointing straight down. There's the FG. The normal force is always going to be perpendicular to the surface. So that always has to be true. And what's going to happen, this is kind of an odd thing that happens when these things are on inclined planes. The weight of the object, the FG, is going to be greater than the normal force of the object. And we'll discuss that a little bit more, but these two forces are no longer equal here. They can't be equal anymore. What happens is we have this weird little similar triangle thing that we can start drawing. We have FG that points straight down. We have this odd net force that we'll have to account for somewhere. It is pointing down the ramp. And then the normal force, it's the thing that connects everything. So when we start talking about how these things are set up, we have to realize where things are pointed. So for an inclined plane, we always need to be able to resolve the weight of the object into its components, along with all of the other forces acting on the object. So for this object here, we have our mass pointing on here. So I like to draw a little M in there to make sure you know what I'm talking about. But here we have the weight of the object, and we like to say it is pointing straight down always. We know Fg is equal to mg. Here, the normal force is always perpendicular. So we could draw a block here if we wanted, but notice how it's always sitting off at an angle. Now what happens here is we have this way we can set this up. We have an angle with the incline right here. We're going to call that theta. And what we're going to do is we're going to sketch what happens to the weight component. So we're looking at the weight component right here. This guy. He's the weight component, and we're going to break him up into its components. We're going to say it's this part down here. We're going to call that FG parallel to the surface. And then we're going to go this way. And this is the FG perpendicular to the surface. So right now, if we just kind of consider this all, if we draw it this way all the time, it's going to be kind of difficult to get confused there. For the sake of argument, we're just going to say this is always going to be theta. We'll talk about how and why these triangles are similar in class tomorrow, but when we look at that, that's always going to be the same. If we look at how it's Fg is equal to mg, and the way the angles start working out, the Fg perpendicular is always going to be the mg cosine theta. And then the parallel one will obviously be mg sine theta. So this is how this is going to work. We have our inclined plane and be able to break it into the components. These are how this will always work. What's going to change is maybe there's friction pointing up. if it's at rest. Maybe there's something pulling it down, so friction will be pointing down. So it depends on the situation that we're given to figure out what all the other forces are acting on it. So a couple of things to notice, right? Only the parallel component pulls it down the ramp. So it's the parallel component of the weight itself that's pulling it down. And then the perpendicular component is equal and opposite to the normal force. And once again, the perpendicular component is the cosine, right, of the weight. And that's going to be the normal force. And that's going to be important when we start talking about when friction is involved and those kinds of things. So let's do a couple of examples to see how this works. Here we have a block sliding down a frictionless plane, and what is the acceleration of the object? So the first thing we have to do is sketch the free body diagram of what's going on. So I know that I have FG pointing down. I have the normal force perpendicular to the object. I have the FG parallel pointing that way, and I guess I'll use green here. The FG perpendicular pointing that way, knowing that my angle is still 35 degrees or theta. All right, so if I'm looking at this, the net force on the object, it's accelerating down the ramp, so I have to look at everything pointing down the ramp. Here's one of those weird things is we can figure out which way is positive or negative. I'm gonna go ahead and call down the ramp positive just for ease of signs. So it looks like the net force of the object is the FG parallel part, and that is causing the mass to accelerate. So notice my FG parallel, remember we decided that is mg, and that'll be sine theta equal to ma. Notice here, the masses end up canceling, and when I solve for acceleration, I get the following. 9.8 times sine 35. And that gives me the acceleration of the object, which is about 5.62 meters per second squared. We would say down ramp, so it's not too confusing. So sometimes the masses will not be needed, right? So I could just say without giving the mass, right? And it's easy to say, oh no, I can't do the problem. Well, the masses end up canceling in some of these, so make sure we understand where those are coming from. All right, the next one we have is the following. We have something being pushed up a frictionless ramp. How much force is required to push it up a frictionless ramp at a constant velocity? So I already know that the net force on the object is going to be 0. And if I take a look at my free body diagram, I have my FG, it's always going to be pointing down. I have the the parallel and perpendicular components of the weight. I have my normal force pointing straight up. And then I have the pushing force, I'm just going to call it F sub P, pointing up the ramp. So once again, it looks like if my acceleration is going to be 0, it looks like my FP and F parallel are the things that are going to be equal here. So when I'm sketching this out, I have the pushing force is equal to the parallel force. And from here, I can figure out what the pushing force is because I now know that it's just this guy that's going to be used here. So it looks like it's going to be FG sine theta. Looks like I know all the things about it. So plugging everything in here, I have 11, 9.8, and with a sine of 58 degrees. So when I crunch those numbers, I get 91 newtons of pushing force that has to go, and that is directed up the ramp. And that's how these questions go. For this last one, we have a block again sitting on an inclined plane. However, this time there is friction involved. And so the first thing we need to do is take care of the free body diagram. So to do that, we'll first start with the weight of the object. Pull that straight down, call that FG. Then we have the parallel side right here, FG parallel, FG perpendicular. That's my same angle right there. I have friction pointing up the ramp, we'll call that FF. Then my normal force is again pointing up. And on these, we have to remember that the normal force is equal to the perpendicular force here. And because it's sliding down, that means the interaction of my frictional force and my parallel force is the net force for accelerating the mass down the ramp. So to take care of a couple things, we know that the FG parallel is mg sine theta. So to plug all in, we have 15, 9.8, and sine of 40. So we get about 94.5 newtons. Then just for fun, we'll take care of the FG perpendicular. And it is mg cosine theta. So finish this guy off, 15, 9.8 cosine of 40. And we get the FG perpendicular of 112.6-ish. So we have all these forces here. So now we're going to take a look at the net force equation. The net force on the object is mass times acceleration. The net force, it looks like it's the FG parallel. Once again, we'll use down as positive, minus the friction force is the mass times the acceleration. So real quick, we have to kind of look at what the friction is doing here. Remember, friction is mu times the normal force. So that's why we needed to understand what the parallel or the perpendicular force was, because it is equal to the normal force. And so my mu was 0.21, and I figured out what my perpendicular force was already. So my frictional force in this problem is about 23.6 newtons. So now that I know my frictional force, I know what my parallel force is, I have enough information to solve for acceleration. So it's the parallel force minus the frictional force over mass, which should give me the acceleration. So my parallel force is 94.5. My frictional force is 23.6. Mass is 15. After I do all my calculations, I should get about 4.7 meters per second squared down the ramp. And that is how we do these problems with an incline, the wonderful inclined plane questions. So there you go. If you have any questions, let me know. Thanks for watching. Catch you later. Bye-bye.